Okay, let's sit down. We shall start the second speech, and will be given by Edward Witten, who I know for more than 40 years, since 1980. I still remember the first time I met Edward in my office in the Institute for Advanced Study, I think in 1981, when Freeman Dyson got him into my office, and to my great surprise, he gave a very simple proof of the positive mass conjecture, which I was somewhat proud of. At first, I thought it cannot be possible, but then it turns out to be a very important argument. And over years, it becomes didn't quite replace my argument, Rickson, but we developed it in a parallel manner, and now it has become an important tool in general relativity, at least the classical general relativity. Since then, I was very impressed by Ed, and then he kept on developing one by one great breakthroughs in both theoretical physics and mathematics. And he was the major person who applied ideas from theoretical physics to mathematics successfully, and vice versa. Both fields has been flourished and become very important because of his contributions. And I'm fully impressed by him, the best theoretical physics in the last 30 years, well, more than 30 years, and has made fundamental change for our subject. And I'm truly impressed by him. So today we will have him to give the talk called Invitation to Black Hole Thermodynamics.
Thank you. Thanks very much, Yale, for the kind introduction. And I'm pleased to have the opportunity to give this talk, which will be an introduction to black hole thermodynamics, a topic which, as you'll see, some of you will already be familiar with it, but I imagine to many, perhaps the majority in the audience, it's a completely unfamiliar topic. But as you'll see, it's a topic that has roots that go back roughly half a century. Now, there's one thing that almost everyone knows about a black hole. Entering a black hole is a one-way street. What goes in doesn't come out, at least according to Einstein's classical theory of gravity. The picture I've shown here, I've copied here, is a picture of a computer simulation of what it looks like if you're near a black hole and you're looking at the stars that are behind it. So you immediately notice that there's a hole in the picture where you see nothing. That's because the light from behind the black hole that came too close disappeared into the hole. Another fact you'll see is that there's an obvious distortion of the star field around the hole, and that's because of the way light is bent near the black hole by the gravitational field. So for today, though, what's important is just that what goes in doesn't come out, at least according to Einstein's classical theory. So we could say that for a black hole to capture something is irreversible. Once done, it can't be undone, at least in Einstein's theory. But there's an obvious conflict between such irreversibility and the fact that the laws of nature are believed to be completely symmetric between the past and future, or in other words, invariant under time reversal. More technically, I'm referring to CPT. But anyway, it's believed that the laws of nature have a perfect symmetry between past and future, which contradicts the idea that anything is truly irreversible. Well, before worrying about a black hole, let's notice that the same contradiction arises in everyday life. In everyday life, there are all kinds of things that we consider irreversible. For example, breaking an egg is irreversible. Once the egg is broken, we can't unbreak it. There's even a famous nursery rhyme about this in English. Humpty Dumpty is visualized as an egg sitting up on the wall. And once Humpty Dumpty has a great fall, all the king's horses and all the king's men couldn't put Humpty Dumpty together again. Now, why is it that all the king's horses and all the king's men can't put Humpty Dumpty together again? One reason is they probably don't have the technology to manipulate matter at the atomic scale. You'd have to glue all the atoms together in order to reconstruct the egg from the broken pieces. But even if they have that technology, there's a more fundamental problem. It would take an incredible amount of detailed information about the required states of all the atoms in order to recreate the egg. All the king's books and all the king's libraries would never contain enough information. For example, the number of atoms in the egg is roughly 10 to the 24. Let's compare that to a reasonable size of the king's library. If the king's library has 1,000,000 books of 500 pages each and 2,000 letters per page, then the king's library contains 10 to the 12 letters, not nearly enough to describe the detailed state of the atoms making up the egg. Now, since the mid to late 19th century, the understanding of physicists of the irreversibility in everyday life is that it's probabilistic in nature. The laws, because the equations of the fundamental laws of nature are time reversal symmetric, the laws of nature do have solutions in which the atoms spontaneously come together and recreate the egg, which then jumps up on top of the wall, where Humpty Dumpty was sitting at the beginning. But such solutions are incredibly fine-tuned and are very unlikely to be witnessed in practice. Now, the idea of black hole thermodynamics is that the irreversibility that Einstein's theory gives us in black hole physics is of the same nature as the irreversibility when you break an egg. It's probabilistic and describes what will happen for natural initial conditions that we expect to be relevant in the real world, but not for very special fine-tuned initial conditions that are logically possible. If you drop a table or a chair into a black hole, it's very unlikely that the black hole will spit them out the next day, just as it's very unlikely that after Humpty Dumpty falls on the ground, he'll spontaneously be recreated and jump back up onto the wall. But it could happen with a positive but prohibitively small probability. That assertion is the spirit of what black hole thermodynamics says. Now, if this is true, it means that Einstein's theory of gravity, general relativity, his greatest creation, is fundamentally incomplete. It describes the average or typical behavior of matter interacting with a black hole, but not the microscopic details. In the analogy between dropping something into a black hole and breaking an egg, which both appear to be irreversible, Einstein's theory is analogous to what physicists know as a thermodynamic description in which breaking the egg is irreversible, as opposed to a full microscopic description by laws of nature that tell you about the behavior at the atomic level and that are invariant under time reversal. In such a microscopic theory, at least in areas of physics that we understand better, nothing is truly irreversible. Apparently irreversible processes are just processes that are prohibitively hard to reverse in practice. Now, you might be scandalized at the claim based on such simple considerations that Einstein's theory is only an approximation. But there's actually another reason that physicists believe that's true, a more technical reason. Einstein's theory is inconsistent with quantum theory, as you discover if you try to use Einstein's theory plus quantum mechanics to compute, for example, quantum corrections to the orbit of the Earth around the Sun. You'll discover if you try to do that the nonlinear mathematics of Riemannian geometry, which Einstein used in developing his theory, doesn't agree well with quantum theory. Now, this somewhat technical reason to believe that Einstein's theory needs to be extended has actually been resolved, at least conceptually, in the development of string theory over the past half-century. I've explained that side of the story in many previous lectures, but today I'm going to focus on the issues that concern irreversibility in black hole physics. There are mainly two reasons for this choice. One reason is that it's an interesting challenge. I've actually never lectured on this subject to an audience as broad as this one, so it's a fun challenge to try to be understandable. The other reason is that although it will be hard to explain this fully, some of the most exciting developments in recent years involve this side of the story. Now, a dream is that the developments spurred by black hole physics and what I'll tell you today, and also the string theory developments that are spurred by more technical problems in quantum gravity, will somehow make contact with each other. Hopefully one day, but I'm afraid that day is in the future. Now, before trying to tell you more about black holes, I should say a little bit more about how physicists since the 19th century understand irreversibility in ordinary physics. The basic concept is entropy. Roughly, entropy measures disorder at the atomic level. Once one specifies the macroscopic state of a system, the entropy is the logarithm of the number of possible atomic states, the possible microscopic states. Well, what do I mean by the macroscopic state? If we're talking about the water in a cup, and assuming thermal equilibrium is a good approximation, the macroscopic state would be specified by saying how many molecules there are and what is their total energy. For a more complex system, there's more information in the macroscopic state. For example, in the case of an egg, you describe the size, shape, and chemical composition of the shell, and similar data about the interior of the egg. But all that macroscopic data would be almost nothing compared to what it would take for a full microscopic description of the state of 10 to the 24 atoms making up the egg. The entropy is then the logarithm of the number of detailed atomic states that are consistent with the observed microstate. So an irreversible process is just one in which the entropy increases. Let's consider the original unbroken egg sitting on top of the wall. It has a huge number n0 of microstates. But the broken egg lying on the ground has a number n1 of microstates that's much bigger still. And the ratio of n1 over n0 is a huge, huge number, much bigger than the number of letters in the King's Library. The statement that breaking the egg is reversible in principle means the following. Take the broken egg sitting on the ground. It has n1 microstates. If you would manipulate, well, of the n1 microstates, there's a tiny fraction n0 that represents initial conditions of a broken egg that will spontaneously reassemble and jump up on the wall. But n0 is much less than n1. If you could put the broken egg in just the right state, one of the n0 states, it will indeed reassemble and jump up. But in practice, it's prohibitively hard to manipulate all the atoms to put the microstate of the black hole, the microstate of the broken egg in one of the n0 states that would have this magical property. I should stress the numbers here are much bigger than any numbers you usually meet in science. For example, in the case of an egg, n1 over n0 might be something like 10 to the 10 to the 23. Let's compare that to other numbers that you might think are huge. The number of atoms in the visible universe is a mere 10 to the 80 or so. And the age of the universe, measured in the tiniest units that we believe are relevant in physics, is only 10 to the 60 or so. So these numbers, which you might think of as giant numbers, are nothing compared to this n1 over n0, which measures the difficulty of manipulating the atoms making up the broken egg so that it would spontaneously reassemble itself. So at any rate, this is what irreversibility means in ordinary physics. An irreversible process is one in which the entropy increases. Differently put, an irreversible process is one in which the number of possible microstates, given the macroscopic observables, increases, making it hard to undo, because to undo it, you'd have to put the system back in one of the special states it started with. The usual mathematical statement about irreversibility is the second law of thermodynamics. It says that entropy, usually denoted as capital S, is always a non-decreasing function of the time t. And this is a statement that's supposed to be true in practice for physically realizable conditions, but not true in theory for every imaginable initial condition. So a corollary, if S is always non-decreasing, is that a process in which S increases is irreversible, or at least prohibitively hard to reverse. Now, Jacob Bekenstein, inspired by questions from his advisor John Wheeler, asked what the second law means in the presence of a black hole. Remember, it says that entropy always is non-decreasing. But as Wheeler and Bekenstein observed, if you toss a cup of tea into a black hole, the entropy in the cup of tea seems to disappear. Well, Bekenstein wanted to generalize the concept of entropy by assigning an entropy to a black hole in such a way that the second law would hold even in the presence of a black hole. For this, he wanted to assign an entropy to the black hole. Well, the entropy should be a property that only increases. What property of a black hole only increases? It's not true that the black hole mass always increases. For example, a rotating black hole can lose mass if its rotation slows down, and that's even believed to be important astrophysically in powering jets that come from centers of galaxies. But there is a quantity that always increases. Stephen Hawking had just proved the area theorem, which says that the area of the horizon of a black hole can only increase. The horizon is the surface of no return. If you cross it, you can't come back, at least according to Einstein's theory. And Hawking had proved that the area can only increase. So the area, I hope you can see it. I'm afraid the whole picture looks black, so it might be hard to see from where you're sitting, that there's a disk here that's completely black, whereas outside of the disk you can see some starlight from behind. But anyway, the horizon is the surface of no return, and Hawking proved that the horizon area can only increase. So it was fairly natural for Bekenstein to propose that the entropy of a black hole is a multiple of the horizon area. For example, according to Einstein's equations, a spherically symmetric black hole of mass m has a horizon radius 2gm, where g is Newton's constant. So its horizon area is 4 pi r squared, which works out to what I've written, 16 pi g squared m squared. However, entropy is a pure number, and area, of course, has dimensions of length squared. So to make a formula that made sense, Bekenstein needed to use fundamental constants to make a unit of area. So his formula, well, as a relativistic physicist, I usually set c to 1, but his formula, including the factors of Newton's constant g and Planck's constant h bar, this was his formula for the entropy of a black hole, except that he didn't know the constant 1/4 that was provided later by Stephen Hawking. So anyway, Bekenstein proposed that a black hole has this area and then entropy, and then he showed that when you toss the cup of tea into the black hole, the increased area of the black hole because of its gain in mass is such that the total entropy increases. So tossing a cup of tea into a black hole is irreversible according to Einstein's equations. And so we would like to believe then that means that the entropy increases. And if you assign this entropy to a black hole, this Bekenstein-Hawking entropy, then you find that the entropy of the original black hole plus the entropy of the cup of tea is less than the entropy of the final black hole after the black hole has swallowed up the cup of tea. Now, the fact that a factor of Planck's constant appears in the denominator shows that the formula is fundamentally quantum mechanical. If you try to take either Newton's constant g or Planck's constant h bar to 0, this entropy becomes infinite. To make a finite entropy like one expects in real physics, it's very important to have both quantum mechanics and gravity. Now, in part because h bar is so small in everyday terms, Bekenstein's black hole entropy is very large. For example, a spherically symmetric black hole with the mass of the sun has an entropy roughly 10 to the 20 times the entropy of the actual sun. So black hole entropy is much bigger than entropies of familiar things that you meet, if according to this interpretation. Bekenstein's idea was that the entropy of a black hole captures the information lost when the black hole was formed. And he proposed a generalized second law, saying that the generalized entropy, which is supposed to be the black hole entropy plus the entropy of ordinary matter and radiation outside the black hole, always increases. So the claim, as I said a moment ago, is that when something falls into the black hole, S out may go down, but if it does, then area over 4g h bar increases by more. Now, famously, Stephen Hawking didn't believe this, but in trying to disprove it, he ended up proving it instead. And I'd like to sketch for you what Hawking discovered. And this was Hawking's greatest discovery. The greatest discovery of Hawking's career was that quantum mechanically, a black hole is not really black. It has a temperature proportional to Planck's constant. As preparation to explain what Hawking did, I want to recall the idea of a Penrose diagram as a convenient way to depict and visualize spacetime. So a Penrose diagram is a diagram where you capture important causal relations in space and time with a two-dimensional picture that's visualizable. You assume that space-time is spherically symmetric, and then you plot only two coordinates, the time plotted running vertically. So the vertical direction is time, and the horizontal direction will be space, except I plot space only by imitating the radius, the distance from the origin. So the origin is 0 on the left edge of the picture. That's the origin of spherical coordinates. But Penrose taught us that in drawing this picture, it's convenient to make a conformal mapping. First of all, a conformal mapping that puts infinity at a finite distance. So the edges of this diagram are future infinity. Technically, future light-like infinity here, but I'll just call this curve future infinity, past infinity down here, and spatial infinity is this corner of the picture. But there's one more important thing in drawing this picture. You draw the picture so that radially ingoing or outgoing light rays are at a pi/4 angle to the vertical. So that blue line is meant to be a straight line at a pi/4 angle to the vertical, and it represents the path of a radially outgoing light ray. In Einstein's theory, nothing can travel faster than light, so anything would travel at most at a pi/4 angle from the vertical. You could have a vertical line that just goes in the time direction. That's allowed by causality, but relativistic causality does not allow anything to move at an angle that's more than pi/4 from the vertical in this picture. So what I've drawn here is a Penrose diagram. This was the Penrose diagram from Minkowski space. Now on the next page, I will show the corresponding Penrose diagram for a spherically symmetric black hole. We'll imagine the history of a star that lived for a while and eventually collapsed to form a black hole. So the orange part of the picture is the part of the picture occupied by the so-called world volume of the star. It looks like the star lived at a point in the far past, but that's an artifact of the conformal mapping that enables us to see the picture. So actually the star had a positive size in the past. It's just been compressed to a point in drawing the picture. It occupied a certain region in space-time. Eventually this space-time ends at a singularity, which traditionally is depicted by this wiggly line at the top. Future infinity is again this diagonal line here, and the very, very far future is this point. And the difference of the black hole from Minkowski space is that somebody living at future infinity can't see the whole space-time. Remember, you can only see signals that reach you moving at an angle at most pi/4 from the vertical. So a light ray outgoing could propagate to the observer at infinity on this diagonal line, which is the horizon. But if you're past the horizon at a pi/4 angle, you cannot escape to future infinity, to this black line. Your life will end at this wiggly line up here. So an observer watching the collapse of the star to make a black hole will be making observations at future infinity, which means on this, roughly speaking, on this line up here, ending at this point. And what we're really interested in here is going to be what it will look like long after the black hole formed. And that will be studied by an observer who will be living just near this corner of the diagram. Now, causality tells us that in general, what there is now followed by what there was at an earlier time by solving the laws of nature, whatever they are. So in particular, the measurements that an observer makes up here can be deduced from initial conditions on what is called an initial value surface. And there's a lot of freedom in picking what the initial value surface is, but I've picked this blue curve. The blue curve has the property that its tangent is always at an angle greater than pi/4 from the vertical. So it's what's called a space-like surface. You can think of it as a generalized spatial surface on which you could formulate initial data And whatever we measure at future infinity will follow from whatever there was on this blue curve. I also picked the blue curve so that it intersected the horizon well outside the world volume of the star, where the quantum fields were essentially in their ground vacuum state, because we're far outside of the star. Now, we're making measurements up at future infinity. Maybe we're collecting light that comes out. And the outgoing light rays will travel at the speed of light, which means at a pi/4 angle from the vertical. So these diagonal purple lines are meant to be parallel lines at a pi/4 angle from the vertical, and they're signals that the future observer observes, which originated from the indicated points here on the initial value surface, the blue surface. Well, the question Hawking asked is, what will you see if you watch a black hole from a big distance well after it formed? That means that you're living up here and you're seeing the signals that come out along those purple lines. Part of Hawking's insight was that although the full details of exactly what you see depend on the precise quantum state of the collapsing star, if you ask what you'll see in the far future after transients die down, there's a universal answer. The key point about the picture is that a signal that's received very late, which means very close to this upper corner of the picture, originated very close to the horizon. You know, if you're past the horizon, you never emerge. If you're just outside the horizon, slightly outside the horizon, you will eventually emerge and be seen by the observer at infinity, but you'll observe at a very late time. So what we see at a very late time, very close to this corner here, originated from the blue curve very close to the horizon. So observations made at late time depends on measurements of the quantum field at short distances. But every state at short distances is equivalent to the vacuum. That's a basic property of quantum field theory. So the late time observations of the observer probe the vacuum state near the horizon at short distances. And that's why Hawking got a universal answer regardless of how the black hole formed. Now we need a very short detour in formulas, which will be more familiar to some than others. I'll try to present the talk so that, okay. There are a couple of slides, and this is one with a little bit more formulas. So here I've drawn again the important part of the picture, the horizon, the far future, the initial value surface, which here, the important part of it is the part just outside the horizon, and here it's drawn in red, and then these parallel bluish-purple lines that are signals reaching the outside observer. Let t be the time at which a signal is detected by an observer at infinity, and let u be any function that vanishes on the horizon. Its derivative is non-zero, and we use it to measure how far from the horizon the signal started. We need to know the relation between u and t, which we get by solving Einstein's equations to determine the propagation of light in the field of a black hole. So as u goes to 0, the time at which the signal emerges gets later and later, and it actually gets later and later logarithmically by this formula. So I won't derive that formula for you. We'll have to accept that that follows by studying Einstein's equations for the behavior of light in the field of a black hole. We can invert that relationship to find that if we make an observation at the time t, it originated at a position u outside the horizon. And you see that if t is large, u is exponentially small. So signals that a late time observer sees originated from exponentially close to the horizon. But what exactly does late time mean? So for example, for a black hole with the mass of the sun, 4 GM would be some microseconds, and so, milliseconds, I think. So if t is 1 second, then this exponential is something like exponential of minus a few hundred, which means that u is incredibly, incredibly small, much smaller. With those numbers, u is just incredibly small. So people build elementary particle colliders to probe the vacuum at distances of 10 to the minus 17 centimeters, roughly, is what the LHC reaches. But if you observe a black hole with the mass of the sun 1 second after it formed, you're probing the vacuum at distances much smaller than that. So as I said already, a basic fact in quantum theory is that at short distances, any state looks like the vacuum state. So Hawking got an answer that's universal, independent of how the black hole formed, and just depends upon the properties of the vacuum at short distances. Now, technically, an observer at infinity would be measuring some kind of quantum field. In the real world, you probably would be measuring the electromagnetic field, because the simplest signal coming out of the black hole to observe would be light. And you'd measure light waves coming out of the black hole by measuring the electromagnetic field. Rather than being realistic as that, I'll just say that we're measuring a quantum field psi of t. And what do you measure of a quantum field? Well, you measure correlations between the quantum field at different times. The simplest correlation is a two-point function, it's called, the expectation value of the product of a quantum field at two different times, t and t prime. To explain Hawking's result, we need a slightly longer detour with formulas. So if you aren't quantum field theorists, you may want to disregard the rest of this slide and part of the next one. Near the horizon, a typical quantum field would have a short distance singularity that's power-like. So for example, for a fermion that has spin half in the 1 + 1 dimensional sense, the two-point function has a simple pole. Then we change variables from the coordinate u that's appropriate near the horizon to the time at which the distant observer makes the observations. We change variables by this formula that we had before. And literally just changing variables from this formula, we get this one. And that, okay, technically I'm hiding something which are called gray body factors, but essentially this is Hawking's prediction for the expectation value of the two-point function of the quantum field of the late time observer. And it has the property that it's anti-periodic in imaginary time, that is, it's odd under shifting the time by 8 pi gm times I, where m is the mass of the black hole and g is Newton's constant. H bar has been set to 1. So anti-periodicity in imaginary time in quantum mechanics is the hallmark of a thermal correlation function, in this case at a temperature which is called the Hawking temperature, 1 over 8 pi gm. So this computation is essentially the one by which Hawking discovered that a black hole has a temperature and emits radiation. So I wish I hadn't said h bar to 1, it would appear in the numerator. The Hawking temperature is h bar over 8 pi gm. And that's the Hawking temperature at which a black hole emits radiation. In other words, a black hole, after transients that depend on how it formed, die down, radiates thermally at this temperature. We can now confirm the value of the entropy. So there's a fundamental thermodynamic relation. When I introduced the entropy before, I told you about the second law, that the entropy is non-decreasing, but I skipped the first law, which says that the change in energy in thermal equilibrium is the temperature times the change in the entropy. So using the first law of thermodynamics, for a black hole, we interpret the energy as being the mass, or more precisely, mc squared. We usually set c to 1, but mass is energy by Einstein's theory, so mc squared is the energy of the black hole. The temperature is h bar over 8 pi gm. So from the first law, we can determine what the entropy must be, and we find that the entropy of a spherically symmetric black hole is 4 pi gm squared. But as I told you before, the horizon area was 16 pi g squared m squared. So we arrive at the Bekenstein-Hawking formula that the entropy is the area over 4g. That's in units where h bar and c are 1. So that's how Hawking confirmed Bekenstein's idea and sharpened his proposal. And once we understand that a black hole can be understood as a thermodynamic object with an entropy and a temperature, we can now understand that the irreversibility when you drop a cup of tea into a black hole is quite analogous to the irreversibility when Humpty Dumpty falls off the wall and breaks. And this basic idea has been confirmed by many subsequent calculations over the last half century. Now, because the black hole has a positive temperature and is radiating at this Hawking temperature, if you have a black hole in vacuum, real black holes in the real world are not in vacuum. They're in galaxies surrounded by other stars, and things are more complicated. But conceptually, an isolated black hole would spontaneously emit thermal radiation, losing energy and evaporating, according to Hawking. But the timescale is very long. For example, a solar mass black hole takes 10 to the 67 years to evaporate, which you might compare to the age of the universe, that's a mere 10 to the 10 years. So we don't expect to observe black hole evaporation, unfortunately, unless we're very lucky in some way. For example, if very tiny black holes were created in the Big Bang, for which we have no evidence currently. We do observe in cosmology something that's believed to be very similar to Hawking radiation from a black hole, namely the inhomogeneities in the early universe that are believed to have been the seeds for formation of galaxies. Unfortunately, there isn't really time to explain that part of the story today. But regardless, Hawking's calculation is of great conceptual interest. Indeed, it poses a puzzle that's driven a lot of research in the half-century since Hawking's work was published. In Hawking's calculation, the radiation that comes out of a black hole appears to be exactly thermal, with no correlation between the different particles that come out of the black hole at different times, except what follows from conservation of energy and from the temperature of the black hole. If that's exactly true, it would mean that black hole evaporation is fundamentally irreversible. It could not be described by fundamental microscopic equations that are invariant under time reversal. To see this, consider a process in which a star collapses to a black hole which then evaporates. If physics is really described by microscopic laws that are fully invariant under reversing the flow of time, the star started in some quantum microstate, and if the equations are truly time reversal invariant, the decay products of the black hole after it evaporates must remember the initial detailed quantum state of the star, because if the equations are time reversal invariant, by reversing the flow of time, you must be able to reconstruct the initial state of the star from the decay products of the black hole. If you had a movie in which a star collapses to a black hole and then evaporates, the black hole then evaporates, you should be able to run the movie backwards. You'd see the decay products come in, form a black hole, which then explodes to make a star. That would be analogous to the broken egg on the floor spontaneously recombining and jumping up on the wall. So it would be a very unlikely process in practice, but if the initial conditions are exactly right, it should happen. And for that to be possible, it must be that the decay products when a black hole evaporates, although they look thermal in Hawking's calculation, actually somehow encode the information of the initial state of the black hole, the initial state of the star. The state of the outgoing particles cannot just be thermal. There must be subtle correlations that contain the information needed to reconstruct the detailed state of the original star. Now, a clue is simply that black hole entropy is so big. For instance, as I remarked, the entropy of a black hole with the mass of the sun is much greater than the entropy of the actual sun, by a factor of 10 to the 20 or so. Many researchers have thought that somehow a black hole having an entropy proportional to its surface area, the area of the horizon, means that the black hole can be described by some sort of degrees of freedom that live at its surface, with 1 bit or qubit for every 4G of area. For example, in a famous article in 1992, John Wheeler illustrated that idea with this picture, where he visualized the black hole horizon being built out of cells of area 4G, and each cell is supposed to contain a bit. I hope you can see that each little cell is labeled by 0 or 1. I'm not certain if it's big enough to be seen, especially from the back of the room. Wheeler talked about bits, but you have to know that the term qubit for a quantum mechanical bit hadn't yet been coined in 1992, so he couldn't have called them qubits. And if you read the article, it's clear that his bits arise from measurements of what we would now call qubits. Now, Wheeler published this article in 1992, but he had been Bekenstein's advisor, and I'm pretty sure he'd been drawing this picture for many, many years before 1992. What I've described up to this point is basically the concepts of black hole thermodynamics from the 1970s. And I've left myself 18 minutes to try to tell you some more contemporary developments. Now, the more recent developments from the 80s all the way to the present involve a somewhat different notion of entropy that's natural quantum mechanically. It even makes sense classically, but I won't have time to explain that. I'll have to be rather schematic because time is short, and also the mathematical concepts involved are more elaborate than what I've been explaining so far. In quantum mechanics, there is an uncertainty principle. A state that has minimum uncertainty, assuming that all possible measurements are considered, is called a pure state. A mixed state is roughly a state that has more uncertainty than is required by the uncertainty principle. So many of you will know that I'm taking liberties in my characterization of what's a pure state and what's a mixed state. But I believe it'll convey the right idea for those of you who aren't already familiar with the concepts at all, since we don't have time for detailed definitions. The von Neumann entropy measures the difference in uncertainty of the extra uncertainty of a mixed state above the minimum uncertainty required by the uncertainty principle. Roughly, if rho is a mixed state, and it would take n pure states to describe rho, then the von Neumann entropy of rho is log n. So people familiar with von Neumann entropy will know I'm taking liberties again here. The entropy that we've been discussing so far in this lecture is thermodynamic entropy. The relation between them is an inequality. For any quantum system, the von Neumann entropy is no bigger than the thermodynamic entropy. Thermodynamic entropy obeys a second law that I've told you about. In any process that can be realized in practice, it's non-decreasing. By contrast, in quantum mechanical evolution of an isolated system, the von Neumann entropy doesn't change. So for example, suppose I take a cup of water, and which is transparent, and I drip a drop of blue dye into it. And this is an isolated system. The blue color initially is localized, it will spread throughout the glass. As the blue dye is spreading, the thermodynamic entropy will be increasing. That's an irreversible process in practice. Once the blue dye has spread throughout the cup, I can't concentrate it again, except by supplying some, what's called a free energy. Well, I can't make it spontaneously, the dye recollect. But the von Neumann entropy doesn't change. So when the blue dye is spreading throughout the glass of water, the thermodynamic entropy increases, but the von Neumann entropy stays constant. Now, what kind of entropy is the Bekenstein-Hawking entropy? Well, I told you that it increases in irreversible processes. So it's a thermodynamic entropy that obeys a second law. However, it's turned out that the von Neumann entropy is also important in understanding black holes. Well, how does the thermodynamic entropy come in for black holes? An important feature of quantum mechanics is the following. Let A and B be two systems. In general, consider the combined system AB. The combined system AB might be described by a pure state, psi AB, meaning a state with minimum uncertainty and zero von Neumann entropy. Even if that's the case, the individual systems A and B can have a greater than minimal uncertainty with a positive von Neumann entropy. That happens because of a quantum mechanical correlation between the A and B systems. In such a situation, the combined system AB has zero von Neumann entropy, but the individual systems have positive von Neumann entropy and moreover equal von Neumann entropy. In this situation, the von Neumann entropy comes entirely between entanglement or correlation between the two subsystems, and is called entanglement entropy. Now, Raphael Sorkin in 1983 was the first to try to understand black hole entropy from this perspective. Divide space into two regions, A and B. You could make any division, but in the application, B will be the interior of the black hole and A is the exterior of the black hole. The vacuum state of the whole universe is a quantum mechanical pure state, a state of minimal uncertainty. But if we consider the quantum fields only in region A or only in region B, we get a mixed state, rho A or rho B, with a positive von Neumann entropy, which Sorkin tried to calculate. And Sorkin and later his collaborators Bombelli, Cullen, Lee, with Sorkin, found that the von Neumann entropy is proportional to the area A of the boundary between the two regions, but with an infinite coefficient. Now, of course, mathematically, this infinity is a little discouraging. Physicists know that a lot of times, if you ask a question that isn't quite right, you'll run into an infinity, which gets cured with a better version of the question. And what Sorkin proposed is the following. The Bekenstein-Hawking answer was A over 4G. But the Sorkin calculation and the refinement with his co-authors here was done ignoring gravity, which is like taking G to be 0. And infinity times A is the correct answer when G is 0. So the proposal was that Sorkin's calculations were the G equals 0 limit of the Bekenstein-Hawking calculation, and that an improved version of this calculation with G not assumed to be 0 would give the Bekenstein-Hawking answer. Now, 40 years later, a computation just like this has still not been convincingly done. But the idea makes a lot of intuitive sense because it fits well with two ideas. The first is that A over 4G is the irreducible entropy for someone who only has access to the region outside the black hole, outside the horizon. And two, the divergence, the infinity that they found in the entanglement entropy was proportional to the area because it came from short distance, short wavelength modes near the horizon, as if the density of quantum degrees of freedom is 1 over 4G as in Wheeler's picture. So I think most people in the field believe that qualitatively this is right, even though we don't know how to do the correct calculation when G isn't assumed to vanish. Now, despite the puzzles, it was important to appreciate that in black hole thermodynamics, you should consider microscopic von Neumann entropy as well as thermodynamic entropy. Now, this awareness could make one wonder, although historically this isn't exactly what happened, but you could imagine things developing in the following way. You could ask, is there an area law for the von Neumann entropy as there is for the thermodynamic entropy? So in other words, in the classical limit, the thermodynamic entropy is the area of something, namely the black hole horizon, up to a factor of 1 over 4G. Well, is there a sense in which von Neumann entropy is the area of something? Well, there is. The first version was found by Ryu and Takenagi, and there were a lot of later refinements by other authors, which I won't have time to tell you about. The simplest setup is to consider a universe with two ends, where here an end, well, first of all, end is a term used in topology, but it matches the intuitive region. So a universe with two asymptotically flat regions where an observer might live. And let the universe be overall in a state of minimum uncertainty, a pure state. And now let's compute the von Neumann entropy of the part of the universe visible to one observer or the other. Well, the Ryu Takenagi formula in its simplest form says that the von Neumann entropy of the part of the universe that the A observer or the B observer can see is the area over 4GH bar, where now the area is the area of the minimal surface S that separates the two sides. So for the geometry I've drawn a minimal area surface in the interior, and the area of that minimal area surface over 4GH bar is the von Neumann entropy of the part of the universe that this observer or that observer can see, assuming the whole universe is in a state of minimum uncertainty. Now, I don't have time to explain this properly, but I should say that in general, see, I've drawn a minimal area surface in Euclidean signature in codimension 1, but in Lorentz signature spacetime, the generalization is that S is an extremal surface of codimension 2 in a Lorentz signature spacetime. Now, in the real world, a black hole forms from a star whose thermodynamic entropy is much less than the thermodynamic entropy of the resulting black hole. So as I told you, the actual sun has a thermodynamic entropy that's 10 to the minus 20 of what it would be if the sun would collapse to a black hole of the same mass. So the star has a tiny thermodynamic entropy compared to the black hole thermodynamic entropy. Now, one thing we know about the von Neumann entropy of the star is that it is only smaller, because any quantum system has a smaller von Neumann entropy than its thermodynamic entropy. When the star collapses to a black hole, see, an isolated star far away from everything else can collapse to a black hole all by itself. That's a spontaneous evolution of an isolated system. In quantum mechanics, the von Neumann entropy doesn't change in spontaneous evolution of an isolated system. So the von Neumann entropy of the black hole when it's born is the same as the von Neumann entropy of the star, and that's no bigger than the thermal entropy of the star and much less than the thermodynamic entropy of the black hole. So a black hole, when it forms in the real world, has a von Neumann entropy that's very tiny compared to its thermodynamic entropy. So in the real world, a black hole is born in a state with a very tiny von Neumann entropy. Then, assuming the black hole is isolated from everything else, it starts to evaporate. When it evaporates, it becomes smaller, and its horizon area becomes less, so its thermodynamic entropy becomes smaller. On the other hand, as the black hole evaporates, it's no longer an isolated system. It's entangled with the radiation it emits, and Hawking's classic calculation from half a century ago shows, or claims to show, that the von Neumann entropy of the black hole increases as it evaporates. So the black hole starts with a big thermodynamic entropy and a small von Neumann entropy. As it evaporates, this one's going down and this one's going up. And after a very long time, according to Hawking's calculation, they meet and pass each other. But that's a contradiction. As first pointed out by Don Page, the fundamental inequality that the von Neumann entropy can't be more than the thermodynamic entropy is violated when the black hole has roughly lived for half of its life, when it's half evaporated. It would violate this inequality if Hawking's calculation is correct. Now, this contradiction actually inspired a recent improvement of Hawking's calculation. With extensions of the Ryu-Takanagi formula for von Neumann entropy, these authors were able to improve the computation of the von Neumann entropy of the evaporating black hole, getting an answer that makes sense even after the page time. So they showed, you see, so the black hole is born with very small von Neumann entropy, very big thermal entropy. At the page time, they meet. When they meet, that means that the black hole is in perfect thermal equilibrium, even microscopically. Although I would need more time to carefully explain exactly what that means. But what these authors showed is that once perfect thermal equilibrium is achieved by the black hole, it continues to be maintained as the black hole continues to evaporate. So saturating the inequality is a statement of complete microscopic thermal equilibrium. In the rest of physics, once that's achieved, it's very hard to lose it. And these authors did an improved calculation I won't explain the details of the calculation that requires refinements of the Ryu-Takanagi formula, but the outcome of the calculation can be described by saying that once microscopic thermodynamic equilibrium is achieved, it's retained at all later times. Surprisingly to most people in the field, it was possible to improve Hawking's calculation in this way without developing any real understanding of the microscopic quantum states of a black hole. So some of the mysteries that have been with us for half a century are still with us. But some of the questions have been answered, and as that happens, one gets more and more confidence in the basic framework saying that the apparent irreversibility in black hole physics is probabilistic, just like the apparent irreversibility when the egg falls off the wall and breaks. Now, I hope I've succeeded today in giving at least an overview of some of the ideas in black hole thermodynamics and some hints about the remaining mysteries. I regret not having a little more time to be more detailed on the second part of the talk, but I hope I've given you at least some hints. Perhaps some of the students here will play a role in unraveling the puzzles. Thank you.
Well, Era, thank you for the beautiful talk. Let's now have a question time. Any questions? Yeah.
Thank you very much for a very inspiring talk. My question, inspired by your talk, is it reasonable to have a kind of symmetry, a duality between the inside of the black hole and the outside of the black hole? The quantum mechanical description that you were describing, von Neumann entropy on the inside.
Well,
and
I'll give a conservative answer. So a conservative answer is that we don't have any indication of a duality between the inside and the outside, but we do have a dual description of the inside holographically. To try to explain it well would really be another lecture, but in certain situations at least, we have a holographic description that's dual to the black hole interior. And that's also, well, that could have been the topic of a different lecture, and it's part of what gives us confidence. It makes enough contact with the things I did talk about today that it's part of what gives us confidence in the story making sense and holding together.
Thank you.
Other questions? Yeah. Raise your hand.
In information theory, people think of entropy as entanglement entropy or von Neumann entropy, but in some microscopic quantum gravity theory, people think of black hole entropy as Boltzmann kind of microscopic state counting. Can you give some comment on these two different concepts of entropy, whether they are fundamentally the same, or one is more general than the other one, or they are just different?
Well, good question. So I didn't explain the inequality I stated, that the von Neumann entropy is no bigger than the thermodynamic entropy. But that comes more or less by investigating your question. So what's called thermodynamic entropy, roughly speaking, thermodynamic entropy is the logarithm of the number of accessible states. And that's also the largest that the von Neumann entropy can be. The von Neumann entropy carries more microscopic information. A cup of water, depending on your assumption, well, a black hole could have a von Neumann entropy as large as its thermodynamic entropy, but in the real world, it's born with a much smaller von Neumann entropy. Okay. I don't feel I'm answering your question very well, so let me take one more try. Von Neumann entropy and thermodynamic entropy agree in thermal equilibrium. But von Neumann entropy is defined universally for any state, not necessarily in equilibrium. For a state that isn't in equilibrium, the von Neumann entropy is less than it could have been, given the macroscopic observations. Well, I hope I've more or less answered your question.
Okay, thank you. Other questions? Yeah.
I want to see if I understand the idea of von Neumann entropy correctly. Can I say that von Neumann entropy measure a system? How close is it being in pure state?
Yes, well, it measures that, but it's not the unique measurement of that. I think it's the most important measurement of that, probably.
Let me follow up.
Yes.
Can I express the difference between the thermodynamic entropy and the von Neumann entropy? We know that's according to the inequality, it's a positive number.
Yes.
Can we kind of describe that as some kind of quantum correction?
Well, it's also true classically that you can define an entropy which in general can be less than the thermodynamic entropy. To save time, I only talked about the quantum version. Well, unfortunately, to save time, I didn't write any formulas that would have gone into defining the von Neumann entropy precisely. And that's why, unfortunately, without having any such formulas, anything I say will be a little bit vague. But the von Neumann entropy is defined for any state of a quantum system. And the thermal entropy is what the von Neumann entropy would be if you're in thermal equilibrium, which means if you have the maximum possible von Neumann entropy given the macroscopic observations. What are the macroscopic observations depends on the system, but for a simple system, it would be energy, angular momentum, charge, things that you can conserve quantities. I'm sorry if those definitely.
Okay, next question. Yeah.
If we assume the eigenstate summarization hypothesis without ergodicity hypothesis, is there any postulate we could be expected? Okay, this question.
I didn't quite hear the question, but I think part of the question is probably whether in some sense a black hole behaves ergodically.
Yes. Is there any postulate about black hole, the seminology, and the seminal hypothesis, some hypotheses we could expect it from the eigenstate summarization?
Yeah. So, well, one of the striking discoveries in the last decade, which unfortunately also would have called for a somewhat different lecture than the one I gave, is that the dynamics of an evaporating black hole is highly chaotic. It's believed to have maximal quantum chaos. So it's believed that a black hole saturates all possible inequalities of how chaotic and ergodic a quantum system can be.
Okay, second question.
Oh, hi, Witten. So do you think that nowadays, how can we use the methods and techniques of quantum information to understand the questions like black hole information and microstates, holography, and the emergence of space-time? Thank you.
Well, I mean, the question was, how can we use notions of quantum information theory to describe black holes? Well, at some level, that's an unsolved problem. But the von Neumann entropy, although I didn't define it technically, is a basic concept in quantum information theory. And the statement that the von Neumann entropy is the area of something is an example of a very limited partial answer to your question. So toward the end of my talk, I was explaining, toward the end of my talk, I was explaining a few of the reasons that people in the field tend to think that what you were asking are good questions. But you were asking questions whose answers aren't really known.
All right. Thank you.
Okay, thank you. So let's end the lecture here. We are starting again at 11. Thank you.